Let me ask you something. What does it take to handle $1.4 trillion in payments every single year? That is Stripe, the company that quietly powers checkout for 78% of the Fortune 100. Amazon, Shopify, BMW, Hertz, Lyft, DoorDash, Substack, millions of other businesses, 47 countries, 135 currencies. On a normal day, hundreds of millions of transactions. On Black Friday, tens of thousands per second. Now here's the question. If you walked into a system design interview tomorrow and the interviewer said design Stripe, where would you actually start? Most engineers freeze, not because they are not smart, because nobody ever gave them a framework. By the end of this video, you will not only have the framework, you will have actually designed Stripe, question by question, from zero to production. Let us go. Here is the framework, 5 steps. Every system design follows them. Step 1. Requirements, what are we building? Step 2. Core entities, the data model. Step 3. APIs, how clients talk to us. Step 4. The high-level design, the architecture. Step 5. Deep dives, the bottlenecks that make or break it. Same 5 steps for Twitter, Uber, Stripe, anything. The mistake most candidates make: jumping straight to drawing boxes before they have agreed on what they are building. Do not be that candidate. Let us start with requirements. First question. What does a merchant actually need from Stripe? Think about that for a second. It comes down to 2 things. 1. Charge a customer. A merchant initiates a payment. We tell them yes or no, approved or declined, in real time. 2. Issue a refund against a completed charge, full or partial. The merchant controls the amount. What about payouts? Sending settled money to a merchant's bank. Mention it, show you know it exists, then call it out of scope. What about disputes? Chargebacks when a customer files with their bank. Same. Out of scope. Mention, move on. Saying these out loud signals to the interviewer that you see the full product, without burning your 45 minutes on side quests. Short pitch. Now the harder question, how fast does it need to be? Here's the number. Every 100 milliseconds of checkout latency costs roughly 1% of conversion. Amazon proved this, Walmart confirmed it. So our target, authorization in under 200 milliseconds at P99, not the average, the 99th percentile. Next question, how much traffic? Stripe processes hundreds of millions of transactions per day, roughly 6,000 transactions per second on average. On Black Friday or Cyber Monday, that spikes to tens of thousands per second. We must design for peak, not average. Now uptime, how available? 5 nines, 99.999%. Why? Because every minute Stripe is down, merchants lose real revenue. If a Shopify store cannot accept payments for 10 minutes during Cyber Monday, that is hundreds of thousands of dollars gone permanently. So 5 nines, 5 minutes of total downtime per year, that is the budget. One more, the tricky one. Exactly once charges. Why does this matter? Imagine the network drops between the customer clicking pay and the response coming back. The merchant retries. Now we are about to charge the same customer twice. That is a compliance violation. That destroys trust. So whatever we build, retries must be safe. The system must guarantee a charge fires exactly 1 time, not 0, not 2, exactly 1. One thing we do not need, strong consistency across every service. For analytics, reporting, ledger settlement, eventual consistency is fine. The fast path needs to be strict. The slow path can be relaxed. But remember that. We will come back to it. Requirements done. Now the data model. Before we name any entities, ask this. What objects actually exist in this world? There is a customer, there is a merchant, there is a bank. But we do not own those. The question is, what objects do we own? First object, payment intent. Why this name? Why not just call it payment? Because the intent to charge is separate from the actual charge. The intent is created the moment the customer hits the pay button. The charge happens after the card network responds. Network can fail in between. So we need to track the intent independently. A payment intent holds the merchant ID, the amount, the currency, the status, and critically, the idempotency-key. We will come back to that. Second object, charge. A charge is created the moment the payment intent is confirmed with the card token. It stores the processor response code from Visa or MasterCard and the final authorized amount. The charge is the receipt. The payment intent is the request. Third object, ledger entry. Every financial movement generates two ledger entries. A debit from one account, a credit to another. Why two? Because of double entry bookkeeping, the same principle the banking industry has used for 500 years. It is non-negotiable for any system moving real money. If you only write one side, your books can lie. Two entries means the math always has to balance. If the sum of debits does not equal the sum of credits, something is wrong and you can find it. Notice, the data model is small. 3 objects. The complexity is not in the schema. The complexity is in the guarantees we have to make when writing these objects under failure. Network drops, server crashes, card network timeouts. That is what the deep dives are for. First, let us design the API. How does the merchant actually call us? Let us design the API. First endpoint. The merchant wants to create a payment. What should we call it? Post/v1/payment_intents. What does the merchant send? Amount, currency, and an idempotency-key in the header. What do we send back? The payment intent object, plus a client secret. Why a client secret? Why not just an ID? Because the next call comes from the customer's browser, not the merchant's server. We do not want the merchant's full API key exposed in browser JavaScript. The client secret is a short-lived token, scoped to exactly this one payment. The browser uses it to confirm directly with us. Second endpoint, confirm. Post/v1/payment_intents/id/confirm. This is called from the browser. Through stripe.js, what does it submit? The card token, never the raw card number. We will come back to why in the high-level design. What do we return? Synchronously, approved, declined, or requires action. Requires action means 3D secure. The bank wants the customer to authenticate. Third endpoint, refund. Post/v1/refunds. Body has the charge ID and optionally the amount. Omit it for a full refund. Specify it for a partial. So, now the interesting design question, set keys. Why is the idempotency-key in the header, not in the request body? Because idempotency is a protocol concern, not a business concern. It applies uniformly to every write endpoint. Putting it in the header means one piece of middleware can enforce it globally, before the request ever reaches business logic. Body fields belong to the business. Headers belong to the protocol. Mix them up and your middleware has to peek into every endpoint's body schema to extract the key. That is a design smell. This is exactly how Stripe ships it in production. Now, let us draw the full system. Question: what is the simplest possible system that could process a payment? Just 3 things: browser, merchant server, bank. The merchant sends the card to the bank. Done. Of course, nothing real works that way. So let us discover one problem at a time why every box exists. Problem 1. PCI compliance. If the merchant server ever touches a raw credit card number, the merchant is now in PCI DSS scope. Hundreds of pages of audit requirements. Every merchant, every Stripe customer. Solution: stripe.js. A small JavaScript library that runs in the customer's browser. The raw card number goes from the browser directly to Stripe servers, never touches the merchant. In return, the browser gets back a short-lived card token. The merchant only ever sees the token. Draw the first box, stripe.js. Problem 2, authentication and rate limiting. The merchant server is calling us. We need to authenticate them. Enforce rate limits, route the request. Solution: an API gateway. Standard pattern. Draw the second box. Problem 3. The actual charge involves 3 things happening together: fraud check, idempotency lookup, Authorization with the card network, SIRE. Solution, a dedicated service that coordinates them, the payment orchestrator. Draw the third box. Problem 4, fraud detection. We have a 20 millisecond budget. Card networks already eat 150 to 180 milliseconds. If we run an ML model inline at request time, we blow the budget. Solution, a separate fraud engine, pre-computed features. We will deep dive on this. Draw the box. Problem 5, money movement. We have to write the charge and the ledger entries somewhere, atomically. Solution, the ledger service, backed by a relational database that supports serializable transactions. Draw it. Problem 6, the card network itself. Visa, MasterCard, American Express. They sit outside our infrastructure. We talk to them via legacy protocols. They can decline. They can time out. They do not support distributed transactions. Solution, we treat them as an external dependency. Draw the card network box on the right. Last problem, webhooks. The merchant wants to know when the charge settled, when a refund completes, when a dispute opens. We need to deliver events to them reliably. Solution, a webhook worker that picks up events from a durable queue and delivers them via HTTP post. Draw the last box. 8 boxes, each one earned its place by solving a real problem. Now, let us walk the charge flow, end to end. Customer types the card. Stripe.js tokenizes. Merchant calls payment intents. Gateway auth and rate limit. Orchestrator runs fraud check, idempotency lookup, and card network auth. In parallel, card network responds. If approved, orchestrator writes charge and ledger entries in one database transaction, then queues a webhook event. Gateway returns the result to the merchant. In under 200 milliseconds, the webhook worker delivers asynchronously. Functional requirement solved. Now let us make this production grade. Deep dive 1. Idempotency. So, picture this scenario. The merchant calls our charge endpoint. The customer's card gets authorized. We write the charge. We start to write the response. And right then, the network drops. The merchant does not get the response. Did the charge succeed? Did it fail? They do not know. So they retry. Now we are about to charge the same customer twice. Compliance violation. User loses trust forever. How do we prevent this? 2 options. Option A. Make the merchant query us first. Status check before retry. What is wrong with that? 2 things. 1. The status query can itself fail. We are right back where we started. 2. We are now pushing correctness logic onto every merchant integration. Hundreds of thousands of developers, many of whom will get it wrong. So dating. Option B. Server-side idempotency. The merchant generates a UID, sends it in the header. We execute the charge, store the result keyed by UU. You what you about what you want you what co is plus merchant ID. On any retry with the same key, we return the stored result without re-executing. Option B wins, but there is a subtle implementation detail that makes it bulletproof. The Idempotency-Key lookup, the charge execution, and the result storage. All 3 must happen inside a single serializable database transaction. Why? Suppose we store the key first, then execute, crash mid-charge. Next retry sees the phantom row and returns false success. Wrong. Suppose we execute first, then store, crash before store. Next retry executes again. Double charge. Also wrong. Only an atomic check right inside one transaction gives you exactly once semantics, with no distributed coordination protocol needed. Exactly once. Solved. Now the ledger. Deep dive 2. The ledger. Question. A single charge has to update 3 things: the charge record, the ledger entries, and the card network must respond. How do we make those 3 writes atomic? The textbook answer: 2-phase commit. Why is that wrong here? Because the card network does not speak 2-phase commit, Visa is not going to participate in your distributed transaction protocol. Full stop. So, what is the alternative? The saga pattern. We break the charge into a sequence of local transactions, each one with a compensating action for rollback. Step 1, write the charge record with status pending. One local transaction. Step 2, call the card network for authorization. Step 3, if approved, update the charge to succeeded and write the ledger entries in one local transaction. If the card network call fails, the compensating action marks the charge failed. No money moves. The ledger stays consistent. Now the key implementation detail. Each next step is written to the database as part of the current steps and stående sekempars Jacomipius state transaction. It tows transactional staged job pattern. If a crash happens mid-saga, we never lose work. A recovery worker reads the staged jobs and picks up exactly where it left off. This is why Stripe can process 6,000 transactions per second against a card network that has never heard of distributed systems. Ledger consistency solved. Now webhooks. Deep dive 3. Webhooks. The merchant wants to be notified the moment a charge succeeds. How do we deliver that event? The naive answer, call the merchant's webhook URL inline during the charge flow. What is wrong with that? If the merchant server is slow, or down, or rate limited, our charge flow blocks. Now their problem becomes our problem. Our 200 millisecond budget blows. The right answer? Enqueue the event into a durable queue inside the same charge transaction, same database write, so it cannot be lost even if the process crashes afterward. A separate webhook worker picks up events, delivers them via HTTP post. If delivery fails, we retry with exponential backoff, 5 seconds, then 30, then 5 minutes, up to 72 hours total. Each delivery is signed with HMAC SHA 256 over the payload and the timestamp. The merchant verifies the signature, so they know the event came from us, not a replay attack. One more critical detail. What if one merchant has a permanently broken webhook endpoint? Do we let their failures slow down deliveries to every other merchant? Absolutely not. Each merchant gets an isolated worker pool. One broken merchant cannot affect anyone else. This is called bulkhead isolation. Same principle as ship hulls. One compartment floods, the others stay sealed. Webhooks solved. Deep dive 4. Fraud. The fraud engine has to decide, approve, or flag in under 20 milliseconds. Why 20? Because we have 200 milliseconds total. The card network round trip eats about 150. That leaves us with 50 for everything else. We give fraud 20. Odd. So the question, can we run a machine learning model inline at request time? Option A, run the model right here, synchronously. Inputs come from the request. What is wrong with that? Inference latency spikes under load. P99 can be hundreds of milliseconds. A single slow prediction blocks the entire authorization. We blow the budget. Customer waits. Conversion drops. Option B, pre-compute the expensive parts. Serve them from cache. Stripe maintains a feature store, a low latency in memory cache of risk signals, updated continuously in the background. Things like velocity. How many charges from this card in the last 60 seconds? Geography. Is this card appearing 3,000 miles from its last transaction? Merchant pattern. Is this amount wildly inconsistent with this merchant's typical orders? At charge time, the fraud engine does one cache read, under 5 milliseconds, then runs a small gradient boosted model. Done. Under 20 milliseconds. Option B wins. If the score exceeds a threshold, route to 3D secure. The customer's bank challenges them. Strong fraud signals get blocked outright. Everything else clears in well under 20 milliseconds. Fraud solved. Let us recap what we built. A payment platform that processes 6,000 transactions per second, under 200 milliseconds with 5 nines availability. Functionally, merchants can charge cards, issue refunds, receive webhooks. Card numbers never touch merchant servers. Here is how each non-functional requirement was met. Exactly once, charges. Idempotency-Keys stored inside serializable transactions. The API layer is safe to retry. Ledger correctness, the saga pattern with transactional stage jobs. Local transactions replace two-phase commit. Every step is recoverable. Webhook reliability, durable queue, HMAC signed delivery, per merchant pool isolation. One broken merchant never breaks anyone else. Fraud under 20 milliseconds. Pre-computed feature store plus a small model. Expensive computation happens in the background, not during checkout. The mental model to take away. Payment systems have two fundamentally different paths. The fast path, authorization, low latency, exactly once semantics, synchronous, strict, the slow path, settlement, payouts, webhooks, tolerates eventual consistency, asynchronous, relaxed. Every architectural decision in Stripe maps to one of those two paths. If you can articulate that separation clearly in your interview, you are thinking like a Stripe engineer. If this was useful, hit like and subscribe. It genuinely helps the channel. Drop a comment with the system you want covered next. I rate everyone. See you in the next one.